Hi, and welcome to Chem '05. Um, Developmental chemistry, which is geared toward pre-health sciences. People who didn't have high school chemistry are the ones who are usually taking this class. So this first unit is just a little bit of an introduction into what chemistry is and why you need to study it. All right, what is chemistry? It is defined as the study of matter and all its properties. Okay, so what is matter? Matter is anything that has mass and occupies space. So basically, it's everything. Everything we can see, feel, touch, things we can't see. It's pretty much the study of everything. So to understand anything, we need to understand chemistry. Sometimes chemistry is called the central science because it is so connected to all the other sciences. You really need to have a good basis for chemistry because biology is based on chemistry. Medicine, geology, the study of rocks has a lot to do with chemistry because the chemicals, the atoms, are the building blocks for everything. So plant science, environmental science, even physics, biochemistry, etc. All right, so first of all, mass versus weight. When we talk about matter is anything that has mass. So what is mass? It refers to the amount of matter in an object. It's very, very similar to weight, but they're a little bit different concept. Mass refers to the amount independent of its location. Whereas weight is a measurement of the gravitational force acting on an object. So a weight is more dependent on the location of an object. So here's the difference. If you had a particular object and you weighed it on the Earth and then you weighed it on the moon, it would have a different weight because of the gravity. There's less gravity on the moon. However, if you had the same object, they would have the same mass in either place. So the amount of what it takes up. Okay, so technically speaking, mass is the correct word that should be used. But just, if you forget what is mass, just to at least think of it as the weight, since pretty much everything we're going to be talking about will be here on the Earth. Okay, so we have a couple of ways of classifying matter. Since matter is pretty much everything, how can we organize it? So we're going to look at two different ways to classify matter. The first way we'll be looking at is by classifying it by their properties. And then the second way will be by what kind of substances the matter is made up of. All right, so properties. There's two types of properties that we're going to talk about: physical properties or chemical properties. Well, a physical property just has to do with an observed measurement of some kind. So you're not changing it. The compound doesn't change to something else. It is what it is. So physical properties are things like color, what state the chemical is in, its density. Well, we'll talk about density later in the semester, but basically density is what's its mass per unit volume. For if you have the same amount of volume of two things, and if one has more mass in that volume, then it is more dense. Some other physical properties: melting point and boiling point. They're very specific to a specific compound, and they describe that substance. You're not changing it to something else. A chemical property, on the other hand, is something that is observed only by attempting to change the composition into something else. So that's when we're talking about a chemical reaction. It's changing to something else. So things that are chemical properties is how does a substance react or doesn't react. So sometimes the fact that something doesn't react is still a chemical property. So flammability. Flammability is an example of a chemical property. So gasoline is flammable. Water is not flammable. So it's still describing that water doesn't break into flames when you put a match to it, but it's still talking about how water reacts or doesn't react. So the ability to react, for example, when you put vinegar and baking soda together, you get a reaction. But if you put vinegar on something else, you may not get a reaction. And then also how something reacts. So, if you burn gasoline, it's going to flame up or possibly explode. But if you burn sugar, it kind of turns black and gives off steam and fizzes. Glass may burn, but it would have to be very hot, and it would kind of, it may melt before it reacts, but how it reacts is a chemical property. Okay, so in the same ways, we can have a physical change or a chemical change. It's very similar, but this is when an actual change takes place. So a physical change is something that takes place without changing what the compound is. So here are some examples of physical changes. Changing of state, if you freeze something or melt something, evaporate, condense. If you take water and you freeze it, it's still water, so that is a physical change. If you take a rock and you pulverize it with a hammer, you're just breaking it up. You're not changing what it is. Similarly, you tear some paper. A chemical change is one that is accompanied by a change in composition. So whatever you start with changes into one or more other things. So a lot of times you can observe a chemical change because there's steam or light or bubbles or like a gas being given off. So some examples of chemical changes: if you burn paper or burn anything for that matter, when you mix vinegar and baking soda, you get a gas given off. That's a chemical change. Even something like ripening a banana, the molecules inside the banana are actually changing. So something is changing into more sugar or less sugar. So they're changing composition. All right, so let's look at a few examples. Determine if the following are physical or chemical properties. Chromium is a steel gray solid. All right, well, if you think about it, it's just a description. Chromium is gray, it's solid, it's steel, colored. So that would be a physical property. Hydrogen reacts readily with oxygen. Well, right there, the word reacts indicates that it's changing into something else, and so that is a chemical property. Nitrogen freezes at -210 degrees Celsius. That is just describing something about nitrogen. Nitrogen changes from the solid to the liquid or the liquid to the solid phase at that temperature. A freezing point is just a physical property. Milk will sour when left in a warm room. Well, if milk is souring, that means it's changing into something else that smells, or it's actually changing composition, so that is a chemical property. Mercury is a liquid at room temperature. Again, that's just a description, so that would be a physical property. Aluminum foil has a shiny appearance. Same thing. It's just describing aluminum foil, so that is a physical property. Gasoline is flammable. Chemical property is saying how does gasoline react. Platinum pin will not tarnish in the air. Again, this one's a little more tricky, but it is a chemical property. Even though it does not tarnish, it's still describing the way that platinum reacts with the air. In fact, it doesn't react very well with the air, but it's still a description of a reaction. So it's a chemical property. Okay, so there's the answers. All right, determine if the following are a physical or chemical change. Frost forms on the lawn. Well, frost forming is just taking liquid and solidifying it, so that is a physical change. Wood is chopped. That is just taking a big piece and making it smaller, so again, that is a physical change. Carrots are grated for use in a salad. Same thing, you're just changing the shape of it. It's still carrots, and so that is a physical change. Malt undergoes fermentation to make beer. Well, fermentation is a process where the malt reacts with something else to give us alcohol. So that is a chemical change. A copper wire reacts with air and turns green. Well, again, the word reacts should signal that that is a chemical change. Bleach removes a stain. This is also a chemical change. The bleach is doing something to the stain and changing it into something else. Sugar dissolves into water. This one's a little bit tricky, but in this case, all that we're doing is we're mixing sugar and water together. We're not changing the sugar, we're not changing the water, they're just mixing up together. We're going to talk about this kind of is called a solution. We're going to talk about that in a little while. But when you dissolve something into something else, it's really just a way of mixing it. So that is just a physical change. Gold is hammered into thin sheets. Again, just changing the shape. So that is a physical change. All right, so there are the answers. All right, the other way that we can classify matter is by the type of substance. So again, here we have matter is everything. What we do is we can say, okay, matter can be made up of pure substances or impure substances. An impure substance is just a mixture of two or more things. A pure substance is one that has a uniform chemical composition throughout the whole substance, and a mixture is a blend of two or more substances. So when we were talking just a minute ago about salt and sugar and water, that they are a mixture. It's an impure substance, but they are each of the substances retain their own chemical identity, and they're just mixed together. So all right, pure substances can be further classified. We have elements. An element is a fundamental substance that cannot be broken down chemically into anything smaller. We can further classify elements by type, which we'll talk about later in a little while and in another chapter. But an element is also found, which we'll see in just a minute. An element can be found on what we call the periodic table of the elements. If something's not on the periodic table of the elements, then it's not an element. It would have to be either a mixture or a compound. So a compound now is a pure substance that can be separated into simpler substances by undergoing a chemical change. So for example, water is a compound. Water is made up of H2O, is this formula H2O. It's made up of hydrogen and oxygen. So you can take water and you can't pull the oxygen and hydrogen apart from each other physically, but you can pull them apart chemically. Like if you put electricity in it or something, you can separate the hydrogen and the oxygen. So a compound is a pure substance because the only way you can separate the hydrogen and the oxygen in the case of water or whatever compound you have is by undergoing a chemical change. And a compound is made up of two or more elements. All right, some other terms that you should know. Homogeneous. Homo means same, and so homogeneous means that the substance is consistent throughout. It looks the same everywhere. Heterogeneous is something that is not consistent throughout. So non-pure substances can be classified as homogeneous or heterogeneous. Elements and compounds are homogeneous by definition because they're only one thing. All right, so here's just a summary. Matter, we have pure substances and impure substances, which are mixtures. Pure substances could be either elements, like we'll see in a minute on the periodic table, or compounds, which are elements chemically combined with each other. And then you can see here elements can actually be further divided. There's metals, nonmetals, noble gases, different types of elements, but we'll focus on that in a couple of units from now. All right, and then impure substances can also be divided into homogeneous mixtures, which is something that looks the same throughout. So for example, if you put salt in water and you mix it, if you look at it, you won't be able to pull out the salt and the water separately. All right, so let's talk a little bit more about our pure substances. The difference between a pure substance and a mixture, it has to do with this topic right here. Pure substances have constant composition and a fixed set of physical and chemical properties. And as we said earlier, pure substances cannot be separated by physical processes. An example is pure water. So, like I said a minute ago, water always contains hydrogen and oxygen, and it's always in the same ratio, 2 to 1. So no matter where I get water from, if I get it from the ocean or the lake or my faucet across in the China Sea, it's always going to have 2 hydrogen to every 1 oxygen. So that is constant composition. And then it has the, a fixed set of physical and chemical properties. Water always freezes at 0 degrees. It always boils at 100 degrees Celsius. Pure water is always clear. It's colorless. It's a liquid at room temperature. So those are physical substance properties that a pure substance has. There's also some chemical properties that will be the same. So water does not react with fire. Water can dissolve many things. The main thing is that water is only one kind of molecule present, and so it is a pure substance. Another example is gold. Gold is a pure substance. Gold is a soft metal, so that's some of the physical properties. It has a melting point of 1337 degrees Celsius. A chemical property is that it will not tarnish. And now gold is an element, and so it always has the same proportion. There's just 1 to 1 to 1 to 1. There's always one gold atom. And so in fact, the solid gold has a regular pattern. Now, on this page, we have a pure substance that is a compound, water, and then we also have a pure substance that's an element, gold. But they're both pure substances because they have a constant composition and a fixed set of physical and chemical properties. Okay, so just going just a little bit deeper. So like I said a minute ago, elements are pure substances that cannot be broken down chemically into simpler substances. They can't be broken down physically either. They can't be broken down in any way. They are the simplest substances known. There are 118 known elements. Each element has its own symbol made up of 1 or 2 letters. We'll see that in just a second. If you have a periodic table printed already, you can look at it. The first letter is always capitalized and the second letter is always lowercase. So make sure you don't make the second letter capitalized because you can get really confused. For example, if you have the compound carbon monoxide, that has the formula CO, capital C, capital O. So that would be carbon and oxygen bonded together. The element cobalt has the symbol capital C, small o, and that would stand for cobalt alone. So, you have to be careful that when you have one element that has a second letter, that the second one is always lowercase. The periodic table of the elements, which I'll show you in just a minute, shows all the elements. If you are looking at something and you wonder, is it an element? If it's not on that table, then it's not an element. It must be a mixture or a compound or something else. A lot of the symbols might not seem like where'd they come up with these. Gold, for example, has the symbol AU, and you wonder where's that come from? Well, it's usually a Latin root, or so aurum. Silver comes from argentum. Mercury comes from hierogyrum. Tungsten comes from a German word, wolfram, so that's why it's got the W symbol, and so forth. Oh, interesting, plumbum, you see lead, plumbum, and you can see the root of the word plumber in there because plumbers originally worked with lead pipes, so that's kind of an interesting side thing there. If you are looking at my PowerPoint, you can then click there for a list of elements by name. That takes you to a website that has all the elements and some interesting facts about each element. But on this slide, I've listed the elements with their symbols, and I've given you sort of a, in parentheses, if it came from some other language, where the symbols come from. And so this is the first half of the elements, and then the second half of the elements. And I have listed them alphabetically with the name of the element, so that, because sometimes it's hard to find the symbol if it has a very different name from the element's name. So you should be able to use this alphabetically if you're looking for the symbol for an element. Okay, and there's a picture of the periodic table of elements. You can see here that if you want to download your own copy, there's a www.science-teachers.com, and you can find a printable periodic table. Actually, there's another website, I think I have a link on Blackboard, which is called webelements, all one word, .com, and you can find another nice periodic table there that you can download. And so you can see, and we're going to talk more in the future about how this table is organized, but for right now you can see that the symbol is in the center, and then the name of the element. Some periodic tables don't have the name, but this one does, and then some numbers, which again we'll talk about later. But if something that you're looking for is not on this table, then it isn't an element. If it's on this table, then it's an element. All right, so a compound is a pure substance, but it's made up of two or more elements chemically combined. And a molecule is the smallest particle that the pure substance, the smallest particle of a pure substance that has the properties of that substance. If you break a molecule up any smaller, it will no longer be the same substance. So like I said earlier, water is a pure substance. It's made up of hydrogen and oxygen. H2O is a pure substance. The H2O is the molecule. If I wanted to somehow break apart the hydrogen and the oxygen from each other, that would have to be a chemical process to do that, and then I would have two different pure substances, hydrogen and oxygen. So water is considered a pure substance because it can't be broken down anymore by any physical means. Okay, like I said a minute ago, we can write chemical formulas. A chemical formula is just where we write the symbol for the element, and then we put the number of each element afterwards as a subscript. So you already know that H2O is made up of 2 hydrogen and 1 oxygen, and so that's the symbol H2O. Pure table salt is made up of 1 sodium and 1 chlorine atom, and so the chemical formula for salt is NaCl. Sucrose, which is sugar, it's made up of 12 carbons, 22 hydrogen, and 11 oxygen, all stuck together, so C12H22O11. Glucose, you may know, is C6H12O6. So a chemical formula just lists them. You might wonder, how do you know which one to put first? Well, there are some rules, and at this point, if I asked you something and you put them in the wrong order, I wouldn't count off for it. For the NaCl, we'll learn more of the rules. A lot of them, you just have to know it because you're told. So don't worry about that. All right, let's just talk about some other definitions that you might want to know. So diatomic molecule is just a molecule made up of 2 or more two atoms, not more. 2 atoms is diatomic. Triatomic would be a molecule made up of 3 atoms. Polyatomic molecule is a molecule made up of more than 3 atoms. We can also have molecules that are either made up of the same kind of atom, so like homoatomic molecule means all the same type of atom. So it's actually a molecule made up of the same atom, more than one of the same atom. Look on the bottom, you can see there are a few elements that actually only exist as homoatomic molecules. So hydrogen gas only exists as H2. You can't have a single H all by itself. It doesn't exist in nature. Same thing with nitrogen gas. The nitrogen gas in our air is N2. It's a homoatomic actually diatomic, homoatomic molecule, both of those things. And then oxygen, also the oxygen we breathe is O2, diatomic, homoatomic. F2, Cl2, Br2, I2 are all homoatomic. And then S8, sulfur only exists as with 8 in one molecule. So they are still considered elements, even though they're molecules. As long as a molecule is homoatomic, we consider that an element. A heteroatomic molecule would be one that has more than one kind of atom, so 2 or more kinds of atoms. So H2O would be a heteroatomic atom. H2O, because it has 2 hydrogen and 1 oxygen, would also be considered a triatomic molecule. Carbon dioxide, CO2, would also be triatomic molecule. When we saw on the last page, the sucrose, C12H22O11, would be a polyatomic molecule because it has more than one. And it would also be heteroatomic. So water is also heteroatomic. So you get the drift there. And then finally, we have mixtures. Mixtures are combinations of 2 or more pure substances that can be separated by a physical property. So the difference between a pure compound and a mixture can be seen right here. Mixtures can vary in composition and in properties. So for example, if you took a glass of water and you put 1 teaspoon of sugar, and then you took a different glass of water and you put 2 teaspoons of sugar, the ratio would be different. The properties would also be different because the one with 2 teaspoons would be more sweet than the first one. The one with 3 teaspoons of sugar might actually be more cloudy than the other ones. So the properties are different. You can vary the composition, and then you can separate the sugar and the water by each other by a physical process. For example, if you took the sugar water and you evaporated all the water off, you would have the sugar left. So that's a physical property, just changing the state. Another example of a mixture would be salt and pepper mixed together. It's a mixture because you have 2 different things. You could have various ratios. You could have a whole cup of salt and just a few grains of pepper, or you could have an even mixture of salt and pepper. Their taste would be different, the color would be different, so their properties would be different. And you can separate them by a physical process. Probably the only one you could think of is to actually go through and pick them apart, but that still is considered a physical process. Now, we can have homogeneous mixtures, which sometimes we also call solutions. A homogeneous mixture is one that is mixed throughout. So this picture here, at first it's not homogeneous, but once we put something in there and we mix it all together, and now you can see the very last one, it's purple throughout. That would be homogeneous. Everywhere you took a sample from or everywhere you looked would look the same. That's homogeneous. In fact, sometimes you can't even tell if something is a pure substance or a homogeneous mixture just by looking. So, if you made a sugar solution and you looked at it and you looked at pure water, you might not be able to tell without tasting it whether it's pure water or a homogeneous mixture because it looks the same throughout. And then, of course, a heterogeneous mixture would be one where it depends on where you took the sample from, the location. When you look at it, you see different pieces. And so you can see here that some fruit jello is heterogeneous because you can see the different parts. If you took a spoon from the right-hand side, you might get an apple. If you took it from the left-hand side, you might get a grape. If you took it from the center, you might just get jello, etc. All right, so here's a nice little summary of the classifications of matter. And you can go through this flow chart. So we have matter. Is it uniform throughout? If it's not, then it has to be a heterogeneous mixture. If it is uniform, then it's homogeneous. All right, but that doesn't tell us everything. So now, if it's homogeneous, does it have a variable composition? If it does have a variable composition, it must be a homogeneous mixture. If it does not have a variable composition, it has to be a pure substance. Then, can it be separated into simpler substances? If yes, it's a compound. If no, it's an element. So I hope that can help you just tell the difference between different parts of matter. So, just one little example. Let's think about if we have the solid elemental, and notice I highlighted elemental, solid elemental phosphorus. It's deep red in color, so that would be a physical property of elemental phosphorus. Its color is red. And then we burn it. While it's burning, a white smoke, which is actually like ash, is collected. All right, so the key word here is that the phosphorus is an element. Remember that elements are only made of one type of atom, one type of substance. So first of all, has there been a chemical reaction? Yes, there has. How can you tell? Well, we see the word burning, we see a change in color, we see smoke being produced. All of those things tell us that there's a chemical reaction. Is the collected white solid different from the original phosphorus? Yes, it is. How can you tell? It's a different color. If it was still the regular, the elemental phosphorus, it would still be red because that is a physical property of phosphorus. Now, because it's changed to something else, because it's turned white, it must be some other compound. Is the phosphorus homo or heteroatomic? Well, since I told you it was elemental phosphorus at the beginning, the original phosphorus would have to be homoatomic, only made up of phosphorus, because it's elemental. If I didn't tell you it was elemental, if I just said some kind of phosphorus compound, then you wouldn't know for sure. It could be pure phosphorus or it could be some kind of phosphorus compound. But since the question says solid elemental phosphorus, then the phosphorus would be homoatomic. Will the white smoke be homo or heteroatomic? Well, sometimes you won't be able to tell, but like I said a minute ago, if the fact that the original phosphorus was elemental and all by itself, then because it burned and it reacted with something, the white smoke is something different, then it would be a pretty good guess that the new compound would be heteroatomic. So probably what's happening is the phosphorus is combining with oxygen or some other element to make a compound, a heteroatomic. Now, there are very rare times where one element can turn into another form of itself, but when we're saying burning, smoke, that is a reaction, which means that that phosphorus is combining chemically with something else. So just something to think about. So there's the answers that you can go through on your own. And that is the end of Unit 1. So I hope you're ready to work hard this semester, and I hope that you've got a little bit of an idea of what chemistry is.